If doctors need to look deep inside your body, they face an immediate physical problem. They need a way to penetrate the skin and dense tissue to see what's wrong, without causing cellular damage in the process. For decades, the standard tool has been the X-ray, or its three-dimensional counterpart, the CT scan. These modalities fire ionizing radiation in a straight path through the body. The radiation passes easily through soft tissue to strike a detector, but gets blocked by dense objects like bone, creating a high-contrast shadow. The magnetic resonance imaging scanner, or MRI, relies on an entirely different mechanism. It utilizes powerful magnetic fields and radio waves to generate highly detailed maps of soft tissues, exposing the patient to exactly zero ionizing radiation. It manages this by ignoring your bones entirely. Instead, the MRI looks for the most abundant molecule inside you, water. To safely visualize a human organ, the scanner abandons the macroscopic world. It reaches down to the cellular level to manipulate the quantum behavior of the water molecules floating inside your tissues. This technical diagram illustrates our primary target, the nucleus of a hydrogen atom. Because hydrogen has a single proton, it possesses a property known as spin. This causes the proton to act like a microscopic bar magnet, randomly orienting itself. When a patient slides into an MRI machine, they are entering a massive superconducting magnet, which you can see represented in the schematic by the large outer rings. This generates the primary magnetic force, known as the B0 field. The sheer power of this primary magnet immediately overpowers the random orientations of the hydrogen protons inside the patient. It forces millions of these microscopic magnets to snap into strict alignment along a single axis. A very small fraction of these protons will actually point in the opposite direction, like walking on their hands instead of their feet, but the vast majority align exactly with the machine's magnetic field, creating a strong net magnetization. This physical reaction establishes a critical baseline. By forcing the hydrogen inside your body into a unified magnetic state, the MRI creates a blank quantum canvas that it can now actively control. To make those aligned protons return useful information, the machine has to knock them out of their aligned state. It achieves this by firing a burst of radio waves, an RF pulse, into the body. This requires resonance. The RF pulse is tuned to the exact precessional frequency of the hydrogen protons, known as the Larmor frequency. If the frequencies match, energy transfers directly from the radio wave to the proton. Absorbing this radio energy forces the protons to tip sideways, violently knocking them out of alignment with the main magnetic field. Then, the RF pulse is suddenly turned off. Left alone in the massive magnetic field, the protons immediately begin to relax, snapping back into their original alignment with the main magnet. As they relax, the protons release the radio energy they just absorbed, emitting it outward as a tiny radio signal. Specialized receiver coils built into the MRI machine detect these tiny returning radio signals, capturing a phenomenon known as free induction decay. By carefully choreographing this absorption and release of radio frequency energy, the MRI briefly turns the silent water molecules in our tissues into active radio transmitters. The body is now emitting millions of overlapping radio signals at once. The machine hears the noise, but it doesn't know exactly where inside the body each signal is coming from. To solve this, engineers installed a set of 3 orthogonal gradient coils. As marked by the red arrow in this cross-section, these sit just inside the main magnet, surrounding the patient on the X, Y, and Z axes. These coils rapidly turn on and off to slightly alter the main magnetic field locally. This violent electrical pulsing is exactly what causes the famous, incredibly loud banging noises during an MRI scan. Pulsing these gradients effectively slices the body into a 3-dimensional grid of individual units called voxels. The gradient alterations assign each returning signal a highly specific frequency and phase, giving it a spatial address in what physicists call K-space. All this raw, chaotic radio data is fed into a computer. The system applies a complex mathematical formula called a Fourier transform, which takes the massive overlapping waveform and isolates it into distinct individual frequencies. Because the gradients assigned a specific frequency to a specific location, the computer can trace each isolated wave back to its exact point of origin, calculating the tissue density based on the signal's strength. The computer compiles this vast grid of located signals, rendering a pristine, high-resolution cross-section image of the internal organs. Through spatial encoding and complex mathematics, the machine translates a chaotic chorus of radio waves into an exact three-dimensional map of human anatomy. Aligning billions of hydrogen protons simultaneously requires an immense amount of physical force. To operate, the MRI's magnetic field must be tens of thousands of times stronger than the magnetic field of the Earth itself. Because it uses supercooled coils to maintain zero electrical resistance, the main superconducting magnet is always on, 24 hours a day, 7 days a week. Even when there is no patient in the room, the magnetic field is active. This creates an invisible threshold extending outside the physical machine, known as the 50 Gauss line. Cross this line, and the attractive force of the magnet becomes significant. Any ferromagnetic object that breaches this perimeter, from a tiny watch or an oxygen cylinder to a heavy commercial floor buffer left by a cleaning crew, will be violently accelerated into the magnetic field. This is known as the projectile effect. The extreme danger of this constant magnetic pull is the reason rigorous patient screening is mandatory. Pacemakers, artificial joints, metal fragments from prior surgeries, and even certain metallic tattoo pigments must be accounted for before anyone enters the hazardous zone. The main magnet forces the protons into alignment. Then, targeted radio waves knock them down. As they relax, the protons emit localized signals, and a computer mathematical formula builds the final picture. The strict safety protocols and the physical hazards of the environment are the necessary trade-off for harnessing this technology. It allows doctors to look deep into our biology without causing a fraction of the cellular damage left behind by traditional radiation. The MRI leverages quantum physics, electromagnetism, and computing to save millions of lives. For more breakdowns on how the complex machines in our world actually operate, subscribe to Works Revealed.